Okay, in this video I will show you the work kinetic energy theorem. But before, let's think why it's called a theorem and not, for example, the law of universal gravitation or Newton's second law. And that's very important to understand because, for example, when you have Newton's second law, force equals mass times acceleration, what is F? You know that the acceleration is how the object velocity is changing in time. So if you, but what is F is missing, right? So this, you could think this is the mathematics, and you know that is just, and this is the physics part of the equation. So that's why it's a physical equation. It's not a theorem. It's not a physical law. Now, what is the law of universal gravitation? For example, is this is the law of universal gravitation. So this is the physics. So if you are pushing the object with 2 newtons, so if you have friction, etc., that's what is on the left hand side. In the right hand side is mass times the second derivative of the position. Or if you have something like this, this is a real equation or a law, because this is the physics and this is the mathematics. But this is a real physical equation. But the work kinetic energy is a theorem, it's not a law, it's not like it's called Newton's second law, universal law of gravitation, etc. Because it's just a redundancy, as you are going to see in a minute. So the definition of work is force times the magnitude of the displacement times cosine of the angle. For simplicity, let's pretend that the force and the displacement are parallel. So work is force times, and in one dimension to the right. So the block is here and this is here. Delta x is d. Just put it like that for convenience. And change in kinetic energy is 1/2 m final minus 1/2 m initial. And the mass of the object is not changing. That's important. It's not like a rocket or something like this. We have, that's the change of the kinetic energy. All right, so now if we use this kinematic equation, and let's prove it from right to left. So I'm proving it in this direction. If you remember this kinematic equation, I have a video that I explain. You can see that b squared minus b naught over 2 equals a times the displacement, acceleration times the displacement. So I can put this over here. So let me move this. So I have that change in kinetic energy is mass times the difference of the square over 2. And that is a x minus x naught. And by the definition of force, force is mass times acceleration. So this is force times x minus x naught, and that is work. by the definition of work. Okay, so I use this here. And this is work. So changing kinetic energy equals to work. So it's kind of a redundancy. That's why it's called a theorem. You could do it the other way, from left to right. Work is force times the distance. Force is mass times acceleration. And you use the same thing. You use b squared minus from this kinematic equation. So this is the kinematic equation. So you get mass times b squared minus b naught squared over 2. Now distribute, and you get, it would be interesting to see if this works, if the mass is changing in time, which is kinetic energy final minus kinetic energy initial. So either way, you get the same thing. Again, but where this kinematic equation come from, I have a separate video for just that. And this is from this. And the velocity is linear in time. The velocity is linear in time, so the acceleration is constant. So showing this equation, if the acceleration is constant, you solve for t in this equation, substitute it over here, and that's how you get the square of the velocity kinematic equation. That is very useful also in conservation of energy. You see this equation again. So this is the derivation, excuse me, of the work kinetic energy theorem. It's not a derivation, it's left hand side equals right hand side kind of thing.